All right, we're going to start as per the norm. I should walk over by our speaker because he's got the microphone. So as per the norm, we're having some technical challenges, but I think we're all set to go. Thank you, Ryan. He's multitasking speaker. So I'm going to ask our secretary, Swapna, to introduce our speaker for tonight, and then we'll get right into the talk. It's recorded. Thanks.
All right, thanks, everybody. I hope the Zoom folks can hear us. Okay, sounds good. So it's my pleasure to introduce Dr. Ryan Cloutier. Dr. Cloutier is an assistant professor in the Department of Physics and Astronomy at the McMaster University in Hamilton. His research focuses on the detection and characterization of the galaxy's most common planets around its most common stars. These exoplanets are sizes between that of the Earth and Neptune and do not have an analog in our solar system that we could study up close. Dr. Cloutier's interests are in using observational techniques to understand the compositions of these so-called super-Earths and sub-Neptunes to inform our understanding of how these planets form and whether the surface conditions may be hospitable for life. Ladies and gentlemen, Inhabitable Worlds by Dr. Cloutier.
Thank you so much. And thank you all for being here and sitting through these technical issues, which, as far as I understand, anytime I come into a new lecture room, there's supposed to be technical issues. This is what my experience has been. So nothing quite out of the ordinary. Sorry. It's okay. But if I just attempt something. How's that? Oh, no, didn't quite do it.
It's got to be in between.
There isn't, but for some reason the cursor disappears.
Yeah.
So I'm gonna, if you permit me one moment, just to get rid of that. Oh. It's okay. We're almost there. We're almost there. Should I let these folks in?
Yeah, let him in. What the heck?
All right.
He's doing everything. He's letting people into the session.
I just want to. If that's all it takes.
Yeah.
Oh, come on now.
There you go.
There we are. And now, do our slides progress? Our slides do progress. All right.
All right.
Thank you, everyone. All right. Very excited to be here to finally start talking to you about the long path towards finding habitable exoworlds. So myself, as Swapna said in the lovely introduction, I myself study these types of exoplanets, specifically the most common types of exoplanets that we actually have in our own galaxy. So I myself am an observational astronomer. So I approach this problem of finding and characterizing planets from an observational perspective, right? From the use of telescopes, as opposed to some of my colleagues across the hall at McMaster who will use computer simulations to tell you about how those planets form and evolve, for example. I come at this from an observational perspective. I try to find these planets like Kepler 186f. So this is an actual exoplanet. It was discovered with the Kepler Space Telescope. It was actually the 186th candidate planetary system that the Kepler Space Telescope discovered. And this is a wonderful artist rendition of what that planet might look like, right? This is the important part, is it's an artistic rendition of this planet candidate, Kepler 186f. It's a planet in the habitable zone. We'll talk about what that means, but sort of a temperate, potentially Earth-like planet. But it orbits a red dwarf star. It orbits a star that's much redder than our own sun. And that's where the sort of tagline comes in. Is like, where is the grass always redder on the other side? We'll get into sort of what that means, but just to sort of allude it to you, it's because it's around a red star, which is actually what I focus on a lot in my own research, which is, of course, why it ends up on the title slide. But so before I begin, assuming that the clicker works, it's not, it's all right, I don't have to go far. Click, click, click. All right. I want to start with the land acknowledgement. The land acknowledgement for McMaster University. So McMaster University recognizes and acknowledges that it is located on the traditional territories of the Mississauga and Haudenosaunee nations. And it's within the lands protected by the Dish with One Spoon Wampum Agreement. McMaster University's land acknowledgement that I've started to use in all of my talks since I arrived there in September, and today is no different. But let us jump right in, right? Jump right into an image that I'm sure everyone in this room is well familiar with, right? The image of the plane of our galaxy as seen from the surface of the Earth. Okay? So the vast majority of the points of light that you see in this image are, of course, Milky Way stars. They are galactic stars, of which there are approximately 100 billion. And for the past few decades, let's call it the past 2 decades, when astronomers have really started to dive into looking for planets and been successful at finding planets around many of these types of stars, we've been able to measure the frequency of planets. That is, how many planets are there per star? As a function, say, of different types of stars. Small stars, red stars, blue stars, big stars, Dr. Seuss, fine, right? And we've actually been able to measure that on average, every single one of these 100 billion stars probably has at least one planet. Right? That is to say that there are at least 100 billion planets within this image, right? Within the Milky Way galaxy. And so let's extrapolate that a little bit, right? We're just talking about the Milky Way galaxy. Of course, the people in this room know that there are other galaxies outside of the Milky Way. If you extrapolate back to the edge of the observable universe, there's something like 10 to the 22 stars. Right? 10 to the 22. Right? So one with 22 zeros, that number of stars. And if every single one of them has a planet, right? That's 10 to the 22 planets. It's an extremely large number. It's an unfathomably large number, one that I tried to contextualize, and I can't. I can't interpret a number that large. But I came up with this kind of interesting fact. You can search, you can do a Google search for numbers that are that large. It turns out that 10 to the 22 planets in the observable universe is more planets than words that have been spoken by humankind. Yeah, still an unfathomably large number, right? I don't know if that actually helps you contextualize, but it's an extremely large number of planets. Right? And so if we're talking about studying planets from the perspective of the search for life, that's an awful lot of opportunities for life, possibly even like our own, to have emerged somewhere in the universe over the course of its 14 billion year history. Okay. So there are a couple of questions that exoplanet astronomers like myself try to tackle this question, right? The first is, we want to understand how planets form and evolve. Right? And this is an active area of research for different types of planets, gas giant planets, terrestrial planets, everything in between. People like me, for a living, are trying to understand where these planets come from. What are the physical conditions under which they form? And what types of physics govern their evolution? And these sorts of questions are particularly important if we want to get at this second major question in modern day exoplanetary science. Has that been there the whole time? No. It hasn't? Is it going to go away? All right. Understanding how planets form and evolve is particularly important for if we want to get to that second question, which I'll read for you because it's a little bit cut off. Are we alone in the universe? Quite possibly a question everyone in this room, including myself, has asked themselves over some point in their lifetime. Another active field of research. We are actually at the point in humankind where we are making significant technological steps towards actually answering that question of whether or not we're alone in the universe. But in order to get there, we have to be able to contextualize the planets for which we are searching that life. And to do that, we are trying to understand how these planets are forming and evolving. And that's the first question that I want to focus on. So how do we study planet formation? Well, there are a number of different ways. One is in situ. It's to look to our own solar system. This is a picture of a meteorite, a very particular type of meteorite called a chondrite, one of the oldest rocks in the solar system. And this is a sample that actually came crashing through the atmosphere, right? It's a meteorite, went through the Earth's atmosphere, landed on the ground. We were able to collect it. And we were actually able to age date this rock to age date the solar system, right? When was the epoch of planet formation within our own solar system? We get that information from geological samples like this chondrite. It also tells us about the primordial chemical composition of the early solar system. Okay? What were the types of minerals that were available? What were the different atomic ratios in the early solar system that went into forming terrestrial planets like the Earth, Venus, Mars? We get that information in situ by studying rocks from the early solar system. So that's one way to do it. A second way to do it is to actually study the planet formation process as it's ongoing. And so we can't do that in the solar system, right? The solar system we know from the chondrites is of order 5 billion years old. Planet formation happened early on in the solar system, so there's no active planet formation going on locally now. But we can use very powerful telescopes, particularly radio telescopes, like the telescope that took this image, called ALMA, the Atacama Large Millimeter Array, ALMA. Took this image of a young star. Now, the young star is, if I have a laser pointer, the young star is actually at the center, and you don't see a very bright source because the star itself is not very bright at radio frequencies. But what you do see are these bright rings of emission from dust, circumstellar dust, that is orbiting around the central star. That's the material that goes into forming planets. Okay? And you know, if you stare at this long enough, you can probably convince yourself that there are a few concentric rings of basically gaps in the dust brightness distribution. There's a deficit of dust in these concentric rings. And that, we think, is a consequence of giant planets that are forming within this disk. They're basically accreting all of the material in the local annulus of their orbit, and they're creating a dust deficit that we can directly observe, right? We can directly see the planet formation process in action. And this is just one example. It's one famous example. The star is called HL Tau. It was one of the first images that came out of ALMA of these so-called protoplanetary disks. And people looked at it and they said, well, that can't be real. Surely that's an artifact of the image reduction, right? At your telescope, maybe you don't quite know what you're going to get. These rings look so damn perfect that some people didn't believe that they were actual of an astrophysical origin initially. But it turns out that there are many examples, possibly hundreds of examples of these protoplanetary disks with these concentric ring structures that are showing us what planet formation actually looks like in real time. Okay? So we have the solar system. We have sites of active planet formation. And the last thing, which is what I focus on in my research, is actually studying the outcome of the planet formation process, right? Looking at the planets that formed many billions of years after the fact, and looking for trends as a function of certain planetary parameters or certain stellar parameters that we can basically use to invert the problem, trace back in time and say what sort of physics govern the planet formation process in order to produce the population of planets that we see today. And I show a cat because I'm always sort of awe-inspired by the sight of just planets itself. Okay. So this is what I focus on in my research, really, is studying the exoplanet population. Okay. And so here's a cool little animation of, well, actually, it's a little bit out of date, but a subset of the known exoplanetary systems. So all of these little colored orbs whizzing around are known, confirmed exoplanets. Right? Planets that orbit stars other than the sun somewhere in the Milky Way. These are actually known systems. And it's a little bit choppy, but that's because there's so many of them. Worth it for the choppiness, right? The different sizes of the orbs tell you the size of the planet. The different colors tell you about the temperature of the planet. And the actual sizes of the orbits that they're zipping around in this animation are actually physically reminiscent of the size of their orbits around the star. Okay? So the takeaway here, in addition to just the extreme diversity of planets, is that many of these exoplanetary systems, excuse me, are very compact compared to the solar system. So if I try to highlight these sort of concentric circles here, these sort of dashed circles, these represent the orbits of Mercury and Venus. No, sorry, there's Mercury. Sorry, Mercury, Venus, there's the Earth, and there's Mars. And as I go out here, there's Jupiter. And the next one is, of course, Saturn. These are the sizes of the orbits of the planets in our own solar system, compared to the actual physical sizes of orbits of many of the exoplanetary systems that we know of. So the overwhelming trend is that exoplanetary systems appear to be extremely compact compared to the solar system. Right? The solar system looks kind of weird. All the planets are spread out. That doesn't actually appear to be the norm in nature. Nature likes to make these compact planetary systems. So already we're gleaning some demographics information, right? We're learning about what the most common outcome of the planet formation process is. It's not necessarily our solar system, which 30 years ago, that was the only example of a planetary system that we had, right? We thought this is what planet formation makes. It makes 4 terrestrial planets close to the star. And then as you go out, it makes the sort of larger gas giants. That was our picture, but it's completely wrong. And we know it's completely wrong because we went and studied the population of planets in the galaxy on a larger scale. And it turns out that this compact configuration is much more common. So I wanted to highlight one. Let's just zoom in on one. The Kepler-11 system, for example. Right? So the Kepler-11 system has at least 6 known planets. And all 6 of those planets, if they were in the solar system, would fit inside the orbit of Venus. Right? It's an extremely compact configuration, and it's actually a dynamically stable one. Right? You can imagine getting things really, really compact. You have these massive gravitational perturbations that can sort of blow up the system, but you have to be a heck of a lot more compact than that, because it turns out that this is the norm. These sort of Kepler-11-like systems are actually fairly prominent throughout the Milky Way. Okay. So coming back to this question, right? Remember all of these planets, right? Remember these 10 to the 22 planets. It's an insane amount. But many of those systems look fundamentally different from our own solar system. Okay? It's not solely the number of planets. We're actually learning something about their architectures, right? How do those planetary systems differ from our own? And again, if you're coming back to this question of habitability, right? What aspects of the solar system are conducive to forming life on Earth? Now that we're getting a global picture of the architectures of many of these planets, not this many planets, right? Does anyone actually know how many exoplanets we know of? I can tell you it's a heck of a lot smaller than that. 3,000, 4,000, I heard 5,000. Yeah. So I did a little ticker when I did my exoplanet class this past term, where we actually counted every week how much it went up. And it was actually going up by about a planet per day. And I think by the end of the term, we were at like 5,400. Yeah, so let's call it 5,000. So we definitely don't know of all of these planets. But we do know from a statistical perspective that many of them look very, very different from our own solar system. And you can start to ask the question, all right, because they look different, what sort of consequences of the architecture of our own solar system may be important for our own habitability? And then how does that translate to many of these exoplanetary systems that look very different, very compact? Yeah.
Do we have enough data to rule out what the limitations of Kepler in terms of the temporal aspects and the size of planets, including their stars, and really be certain that it'd be very hard to see a Saturn-like system, let's say, this one.
It would be, indeed. And so I can talk about some of those limitations as we sort of move on. But indeed, we do not necessarily have the sensitivity to finding all of the planets in our own solar system. If they existed, if there was a mirror solar system somewhere else, we would not necessarily have the sensitivity to detect all. That's a good point. All right. And actually, this is actually a great segue to the next slide, because here, right, there's a fundamental limitation to finding different types of planets. Okay, so these are the planets in the solar system to scale to our own sun. And the fundamental limitation that is preventing us from finding all of these different types of planets is, well, it's sort of multifaceted, right? It kind of depends on the technique that you use. But fundamentally, there's one big reason that we can't find all the planets and why finding planets is difficult in general. It's that stars are big and bright, but planets are small and faint. That's it. That unfortunate fact is what is preventing us from finding all of the planets that we believe are out there, right? That belief is based on an extrapolation. It's not because we know they are out there. It's based on the statistics that we currently have with these limitations, extrapolating outward. So to give you a sense, I'm going to sort of back up, sorry. So just to give you a sense, Jupiter, for example, is 10 times smaller than the sun in radius, in one dimension, not in volume, but just its radius is 10 times smaller than the sun. Right? Earth is about 10 times smaller than Jupiter. So 100 times smaller than the sun. Right? Jupiter, 10 times smaller than the sun, is about 10,000 times fainter. 10 times smaller, but 10,000 times fainter. The Earth, 100 times smaller, 100 billion times fainter. Right? Not exaggerate. It's 100 billion times fainter than the sun. Okay? And the reason I'm telling you this is just to sort of highlight how difficult it is to find not only these types of planets, but any types of planets, right? There's this fundamental limitation that we don't actually see the planet. They're too small, they're too faint. So we have to rely on indirect methods if we want to find these planets and study them at the population level. And one of the most prolific methods that we have to do that is called the transit method. Okay? So imagine you have a star, and that star has a planet orbiting around it. And the orbit of that planet is oriented sort of edge-on relative to your line of sight. Right? So if I'm a star, if my head is a star, and you guys are all telescopes, if the planet orbiting around my head is sort of oriented edge-on relative to you, if you stare at my head long enough, eventually you're going to see the planet come in front. And that is the basis for this transit method. As the planet comes in front, you don't see the planet, you only see the star, but you'll see the star's brightness sort of drop off in this sort of bowl-like fashion, this dip-like fashion. This feature, this dimming, is what we call the transit event. And you can imagine if the planet continues along its orbit, right, a more or less periodic orbit, you will see periodic transits. Okay? So in this example, where there were two planets, one was sort of terrestrial planet size, the other was more Jovian size. What's that? Sorry, that was a question, right? You'll see that, of course, the amount of light that's blocked is proportional to the size of the planet. Bigger planet will block more light. It'll create a deeper transit effect. Right? So this is one of the fundamental parameters that we can actually measure from the transit, is the size of the planet, right? And right away, that allows you to, at least partially, start to distinguish between giant planets and, say, small terrestrial planets. Okay. So here's an actual depiction of some data. This is some actual data from a space telescope called Corot, which is French, so I'm not pronouncing it correctly. It was a European photometer that went out and was looking for transiting planets. And so you can see there's some sort of, well, there's noise. There's sort of like these sharp, high frequency noise. And then these sort of like long-term trends, which is the star just being noisy on its own. But I think we can all clearly see that there are 6 transits in this data set, all from the same planet. It's the same planet just sort of orbiting around this star with a period that you can measure by measuring the time interval between 2 consecutive transits. Right? So this x-axis here is time in days. So if you measure the time difference between, let's call this transit 2 and transit 3, you can measure that time interval You get something like 9.2 days for this planet. That's the orbital period of the planet. That's the time it takes for this planet to go around its host star. 9.2 days. Right? Very different from the 365 days that we're all used to. So this is the planet that, by virtue of it having a shorter period, is much closer to its host star. By virtue of being much closer, it's much hotter. Right? This planet might be too hot to be habitable, but this is sort of reminiscent of most of the exoplanets that we know of. Remember that animation of all the whizzing little orbs and how compact they are? They had very short periods that you measure from these sorts of transit light curves. Right? And this is important because, again, the period tells you the distance, and the distance tells you the temperature. So from the transit, you can measure very fundamental parameters of these planets. Well, first you can tell that they exist. That's great. That's how we got to the 5,400, right? But you can also measure the size of the planet, and you can measure its temperature. Okay? You can see how we're sort of building up to this question of how are we going to find Earth-like planets? Well, those are two very fundamental quantities, size and temperature. So we're getting, we're building. Periods is distance, and distance is temperature. Where have I heard that before? Okay. So the distance matters for the temperature, of course. And the temperature matters for the concept of the habitable zone, right? This sort of astronomer-defined range of distances from a star over which you expect the temperature of the planet to be such that any water that that planet hosts should be in a liquid state. Okay. So this plot here, so these are different stellar masses on the y-axis. So here we go, we have the sun sort of near the top, and then lower masses down to about 10% the mass of the Earth. And then on the x-axis, we have orbital distance, excuse me. And then this shaded band is the so-called habitable zone. It's the range of distances around different types of stars, where if you had a planet orbiting that star at that distance, you could reasonably expect its temperature to be such that if that planet hosted water, that water would be in a liquid phase. It would be stable surface liquid water, the way we have on Earth. And we believe, if you ask the astrobiologists, this is a critical ingredient for our own habitability. And it's something that's observationally accessible for exoplanets. Right? We can measure the orbital distances from the periods. So we can put these planets on this axis. And of course, we know what the stars they orbit. Right? We know if it's a very low mass star, where these really low mass stars, they're not very luminous, they're not very hot. So if you want your planet to be sort of temperate enough for liquid water to persist, you have to be really close to that star. Whereas if you go to higher and higher stellar masses, those planets are getting bigger, they're getting more luminous. That is, they're giving off more energy. So if you were still very close, you'd be much too hot for water to be stable in a liquid form. It would all be vaporized. So you have to move further away. You have to move to a larger orbital distance as you go around these types of stars. Right? Now, so that's all fine and good, unless you're me or some other observational astronomer who wants to find habitable zone planets. Right? If you want to find a habitable zone planet around, say, a solar mass star, if we sort of say, all right, we're going to stick it around here, and we need to sort of map this down to the x-axis, well, this is something like twice the distance between the Earth and the sun. That's a very long orbital period, right? It's much longer than 365 days. So if you want to measure transits, really you want to measure multiple transits, right? Because if you just see one, well, I don't really know what that is. It could just be noise. Transits should be periodic. So really, I want to see one and then wait one orbital period and see two. And even two is a little bit ambiguous, because how can you differentiate between the same planet going around twice and just 2 different planets whose periods you don't know. Really, you want to see 3 times, right? 1, 365 days later, 2, and then maybe another 365 days later, 3. That sort of gives you the confidence that you're seeing a periodic phenomenon, that you're seeing the same planet and you actually confidently know its orbital period. But it takes of order 3 years. It takes of order a PhD thesis, right? Not too much fun. But if instead of studying Earth-like planets around Sun-like stars, instead you say, all right, I'm interested in Earth-like planets around the lower mass stars, the red dwarfs, the stars that I tend to focus on in my own research. Well, these habitable zone planets are much closer, more than 10 times closer. And the orbital periods that correspond to those distances are no longer 365 days. They're sort of order 10 or a few tens of days. Okay? That's a really fast PhD thesis. That's an impossibly fast PhD thesis. But the point is that these types of habitable zone planets, if you're interested in this question of habitability, these types of planets in this region are much more observationally accessible because they can be detected and characterized on, let's call a more realistic timescale, a more human timescale. Okay? So this is one of the reasons why red dwarfs are actually really exciting. And so here we had this 9.2 day planet. I think it was around a sun-like star, so it's much too hot. And okay, again, I'm talking about the Jupiter radii. And sorry, I don't have my notes here, so if I find myself repeating myself, it's because I don't know where I'm going. We're all in this together. So another reason why I sort of want to hammer this point of why red dwarfs are better than sun-like stars, and of course I'm biased, but hopefully I can convince you by the end of this that it's true. Right? The habitable zone is closer, but also the size of the signal is going to change as a function of the star. Okay? So this is a sort of depiction of the sun, right? So it's the sun, this little O symbol, I don't know if people have seen this before, but this notation is the sun. So this means the sun at 1 solar radius. By definition, the sun is 1 solar radius in size. So if you take a planet, let's say you have a super Earth, and you put it around that star, right? You have a super Earth transiting in front of a sun-like star. The depth of the transit that it creates is going to be 0.03%. That's how much of the star's light is being blocked by this planet. It's a very, very tiny fraction. And the reason it's so tiny is not just a function of the planet, it's a function of the planet and the star. It's because, remember that transit depth? How we said it was a function of the size of the planet? It is, but it's not solely a function of the planet. Because when you measure a transit depth, you're not directly measuring the size of the planet. What you're actually measuring is the size of the planet relative to the star. So this is a relatively big star and a tiny signal. But what happens if you take a different type of star? Well, I'm going to call a high mass red dwarf. So it's lower mass than the sun. It's smaller than the sun. What do we have here? We have 0.5 solar radii. So half the size of the sun. But if you take the exact same planet, but you put it around this different star, you get a much bigger transit signal. About 4 times larger. Still sub percent, but 4 times larger than the exact same planet around a sun-like star. So again, this question of habitability, if we want to focus on terrestrial planets, the so-called super Earths, right? Not gas giants, planets that still appear to have a rocky surface, it gets really difficult around sun-like stars. But those same planets start to become more observationally accessible just by looking around smaller stars. And if you go to the extreme end, if you go to the really low mass red dwarfs, so now 10% the size of the sun, you get quite a whopping transit signal. And take my word for it, 3.5% is a whopping transit signal, right? We can do that from the ground with modest telescopes. Okay? So these types of planets, right, super Earths around red dwarfs, are much more observationally accessible, not only because their habitable zones are closer, but also because the transit signals get larger. Okay. And then the last point I want to make is that if you just look at the opportunities to search for planets, you have to look at the distribution of stars throughout the galaxy. So this is a little depiction of sun-like stars in the solar neighborhood. And I think the research team that actually conducted this study, where they're actually sort of doing a census of stars in and around the solar system, this only goes out to about 40 light years. Okay? So it really is the very, very local galaxy. Okay? And it's so local that you can actually just count up all the sun-like stars here. I think if you count them up, there's about 30 or so sun-like stars within 40 light years of our own solar system. But if then you go and include the red dwarfs, you'll find that they overwhelmingly dominate the local inventory of stars. Red dwarfs actually outnumber sun-like stars by something like 10 to 1. Red dwarfs are overwhelmingly the most common types of stars. The sun is not average. The sun is not typical. The sun is big. Right? The most common stars in the galaxy are these red dwarfs. So very common. Lots of opportunities to search for planets. Big transit signals because the stars are smaller. And habitable zones whose orbital periods correspond to something that you can actually get at over the course of a PhD. So these, I would argue, are the most exciting potential targets for trying to find planets, especially planets that might be potential hosts for life outside of the solar system. And coming back now to this image from the title slide, right? This Kepler 186f, it's an actual exoplanet, a known confirmed exoplanet in the habitable zone of a red dwarf. And the tagline, which is now cut off, right? The grass is always redder on the other side. The reason for that being that you could imagine if there was a biosphere, a vegetative biosphere that had formed on this planet, right? That had evolved on this planet, but not under the input spectrum of a sun-like star, under a much redder spectrum. Maybe that vegetation evolved to optimize the process of photosynthesis using red light, right? So maybe there is vegetation, and this is just an artistic rendition, but if there is vegetation, you could reasonably imagine that it looks vastly different from our own vegetative biosphere, given that the input light that it's using for the photosynthesis process is fundamentally different from what you and I experience. It's much redder. So I think that's a cool little bit of sci-fi. I'm not a sci-fi guy, but I do really like these posters. I have this one actually framed in my living room. I also just like the color red. Go figure. All right. So we talked about the transit method. I wanted to briefly touch on a second highly complementary method to the transit method. So this is a video. I'm going to play it in a second, but I want to sort of set the problem up first. Okay. So once again, you can imagine you have a star, and we have a planet orbiting around that star. But is that really what's happening? Well, not quite. Right? It's not quite that a planet orbits a star. Even in a two-body system, right? Star plus planet. Even in that system, it's not that the planet is orbiting the star. It's that both of those massive bodies are orbiting their common center of mass. The planet has mass, so it offsets the center of mass slightly from the star. Now, not very much, because the star tends to be so much more massive than the planet. It's often true that the center of mass of the system is still inside the star, but it's not at the center of the star. So the star does conduct its own little orbit. And so with this complementary method is you take a spectrum of the star. So all these different colors are, you can imagine shining white light through a prism. I don't know if you've ever seen like the cover of first physics textbooks or read Newton's biography or that sort of thing, right? But if you sort of shoot white light through a prism and it disperses that light into the rainbow, right? All the different colors of light, then you end up with a spectrum. And hello, Rob. That's okay. I just want to highlight some of these black bands. These are atomic absorption features in the star's spectrum. So it's not a sort of, it's not a nice continuum. It's a nice continuum sort of underneath, but then on top you have these absorption bands. And the absorption bands are great because as the star is moving around in its orbit under the gravitational influence of a planet, you will actually see the spectrum, and specifically you'll see those absorption lines sort of wobble back and forth. It's a phenomenon called the Doppler effect. So this is often called the Doppler technique. And so even though you don't see the planet, remember planets are small and faint, even though you don't see the planet, you do see the star. And if you monitor it long enough, you can sort of watch the spectrum of the star wobble back and forth. And the amount that it wobbles back and forth tells you something about the planet. Okay? It tells you about the existence of the planet. It also tells you about the period. So here's some actual data. So it's called stellar radial velocity. It's basically the amount of shift in this wavelength dimension translates into a velocity on the star. And so the star is sort of wobbling with a well-defined period. And that's because if you watch the star long enough, you'll actually see it not only wobble in one direction, but you'll see it wobble back. And if you can see many of these cycles, then you can actually get a period. And we have a very nice period, right? The x-axis is called orbital phase. That's basically what is the phase of the planet going from 0 to 1. So you can get the period, but the amplitude of that variation, right? The amplitude of that sine curve tells you about the mass of the planet, right? It's a gravitational effect, so it's sensitive to mass. Okay? So this is actual data. It's an example of a super Earth around a red dwarf star, and it's creating what we would call a semi-amplitude. So basically this height, which I'm not going to try to strain my neck, but if I look over here, maybe I can convince myself that the semi-amplitude is something like 1 or 2 meters per second. Sort of the speed that you and I walk down the sidewalk. We are able to measure that level of velocity change, that level of precision, and detect the masses of super Earths around red dwarfs. But if you take this same planet, and instead of sticking it around a red dwarf, you stick it around a sun-like star, you get something that looks like this. A little tiny semi-amplitude, right? Sun-like stars are big, more massive. So a planet of the same mass is not able to sort of tug on a large sun-like star to the same extent that it can a red dwarf. So super Earths around sun-like stars start to become inaccessible from an observational perspective. Right? Instead of amplitudes of, let's call it 1 meter per second, around a sun-like star, you end up with an amplitude that's about 10 times smaller. A few to say 10 centimeters per second, which is actually beyond the technological capabilities of the best radial velocity spectrographs in the world today. We cannot detect this super Earth around a sun-like star. Our instruments don't have the precision to do it yet. Okay. So if you want to measure the mass of a super Earth, you are sort of relegated to red dwarfs. Okay. Another reason why they're particularly interesting. And so why would you want to do that at all, right? I mean, we already have the radius, we already have the size. Can't you use that to sort of distinguish between small terrestrial planets and larger gaseous planets? Well, I mean, to first order, yes, but there's some intermediate regime where you'd really like to get both of these. Because if you get the mass from radial velocity and you have the radius from the transit, then you can start to distinguish between an Earth-like composition, right? if you have the mass and the radius, you can actually get the density of the planet and say, oh, this planet is consistent with being dense like rock and iron, versus something that's more like Neptune, which is dominated by sort of low density gas. If you have the mass and the radius, you can start to distinguish between these two scenarios, right? The combination of rock and iron versus, say, rock and iron, plus some volatile ices, plus some gas. And again, this starts to become really important from the question of potential habitability of these planets. At least if you're looking for life like our own here on Earth, that is based on a solid surface. Maybe the surface of these so-called Neptune-like planets that are lower density are not so conducive to forming life like our own. So you really want to get the mass and the radius to really identify Earth-like planets in terms of their bulk composition. And this is how we do it, by combining the transit and radial velocity methods. Okay. So given what we know about exoplanets, right, we said we can measure their masses, their radii, their orbital periods, which tell us something about their orbital distances, which tell us something about their temperatures. Is that enough that we can classify any one of these planets as being habitable? Not rhetorical. No, it's not. Why? They do. There we go. Yeah. Now, yeah, sorry. Right. So we haven't talked about the stars itself. But yes, so things like a magnetic field and an atmosphere. Absolutely. Things that are definitely important for our own habitability. Right? I think this is actually, well, okay. It's aggressive. Okay. I guess I was expecting somebody to say yes. Somebody would say, yes, absolutely we can. The kid in the back. Yes, absolutely we can is often the answer that I get. The answer is no. Shut up, kid. Anyway, no, I'm kidding. I'm kidding. All right. But yeah, absolutely. Why not? So one of the things we said was magnetic fields, right? I think the first one I have here is, oh, it's actually not magnetic fields. Rotation, right? This idea that the planet also has to be rotating at a sort of Goldilocks rate. If it's spinning too fast, it'll actually break itself up. That would be much too fast, right? If it's rotating too slowly, then let's say it's rotating slowly compared to the time scale over which it's receiving radiation from the star. So if its rotation rate was very, very slow, there would be one sort of superheated side of the planet, and then the opposite side would not be receiving very much energy at all. And so you'd have this very steep temperature gradient from a very hot side to a very cold side. Probably not great for habitability. Really what you'd like is a more temperate sort of longitudinal distribution of temperatures. Of course, you can have day-night cycles, but that's the level of a few tens of degrees, not hundreds of degrees like you might expect if the rotation rate was very, very slow. I also, magnetic fields, of course, right? Magnetic fields are important for probably a number of reasons, one of prominent reason might be that, at least on the Earth, the magnetic field, the global magnetic field of the Earth protects us from high energy particles from the solar wind. It actually protects the atmosphere from energetic collisions that can strip the atmosphere over time. So we think in general, a magnetic field is important. And these two factors, neither of which are directly observable, at least for the vast majority of exoplanets. We can talk about some niche cases, but certainly for anything that is potentially habitable, the rotation of an exoplanet, the magnetic field of an exoplanet are completely observationally inaccessible. Okay. Well, what else do we got? I see, the trend. The reason for the big red no and 2 exclamation marks. There are probably a lot of factors that go into dictating the habitability of any individual planet, the majority of which are not observationally accessible. And so you're not meant to read this, although I assume some of you are trying. Right? But they're color-coded by things that are currently observable, sometimes observable. That usually means there are certain niche planets where we can do it, but not habitable planets. And then things that are definitely not currently observable. Right? And so many of those things are the sort of black color. Many of these things are not currently observable, but if they are required to interpret the habitability of a planet, then we have a bit of a problem. Right? we can't for any individual planet say with a high degree of confidence whether or not that planet is likely to be habitable, let alone inhabited. Right? That's a whole nother question. But there are a lot of observational pieces that are missing in this question of, can we find habitable planets? Okay. So coming back to the question of now, are we alone in the universe? How can we possibly get to that? Okay. The things that are observationally accessible about planets are very limited. I think I've made that point, right? But they do tell us a lot about how those planets form and the sort of evolutionary processes, at least a subset of the evolutionary processes that they undergo throughout their lifetimes. And while that's very important for contextualizing the environment under which life might be forming on those planets, the question of, are any of them actually inhabitable, is not currently accessible. So I want to start now talking about, some of the ways that we are going to attempt to approach this from an observational perspective. Despite the fact that there are all those parameters that are not going to be observationally accessible, how can we start to try to tackle this question of, are we alone, by searching for signatures of life? And I'm going to argue that the best way for us to do this as a community, observational astronomers, exoplanet astronomers, is by studying the atmospheres of planets, specifically their atmospheric chemistry. Okay. So this slide, again, very convoluted, but at least will serve to sort of describe the diversity of atmospheric chemistries still in our own solar system. Okay. So I want to draw your attention to Venus and the Earth. Two very similar planets in a lot of ways. Very similar sizes, very similar masses, very similar amounts of energy that are received from the host star. Okay? But vastly different atmospheric chemistries. Okay? Venus, for example, 96% of its atmosphere is dominated by CO2, carbon dioxide. And if you sort of look through the other sort of trace gases, you'll notice that there is no water. And that sort of tells us part of the story. I actually think that Venus lost its water early on in its lifetime. And with a lack of water, Venus wasn't able to regulate its temperature the way the Earth does. Water is a very important catalyst for something called the carbon cycle, which acts to regulate a planet's temperature. And without water, that carbon cycle cannot persist. So what happens over time is volcanism starts pumping CO2 into the atmosphere of Venus, and it gets stuck. It has nowhere to go. Basically, CO2 builds up in the atmosphere, and you get what's called a runaway greenhouse effect. And it makes the surface temperature of the planet extremely hot, extremely uninhabitable. And it happened on Venus, but it didn't happen on the Earth. Despite them being very similar mass, very similar radius, receiving very similar amounts of energy from the host star, from the sun, their atmospheric chemistries look very different, right? Earth is dominated by N2, this fairly inert gas. And then it's got a whole lot of oxygen, right? 24% of the Earth's atmosphere is in oxygen, which actually comes from our own biology. Right? O2, in the Earth's atmosphere, in those amounts, is produced by photosynthesis. It's produced by trees, vegetation. O2 is what you might call a biosignature. It's an atmospheric chemical gas that is produced by life. And I'm going to argue that some of these chemicals are going to be observationally accessible and offer a means of potentially finding a biosignature, could be O2, could be something else, on an exoplanet. Okay? So yes, trees, and then, okay, there's some water in there. There's also methane, which is another important biosignature that I'm not going to talk about, but we also have methane in our atmosphere produced by cows, flatulence of cows. It actually creates a detectable signature of methane in our own atmosphere. And it's a biosignature because cows, as far as I know, are alive. All right. So how do we go about doing this? We're going to do it with a technique called atmospheric transmission spectroscopy. So the schematic is the following. Imagine a star, and it has to be red because Ryan's giving the talk. And then imagine a telescope on Earth. Now, if that red dwarf is giving off light at different wavelengths, of course it does, it has a continuous spectrum, it's giving light, it's emitting light at different wavelengths, but we're only going to consider two wavelengths in this very simple schematic. Okay? So we're going to consider a short wavelength blue wavelength photons, and then we're going to consider longer red wavelength photons. And both of those wavelengths are getting to our telescope. Okay? We can see the star at both of those wavelengths. Now, so if that red dwarf has a transiting planet, well, we know that the transiting planet is going to block some of that light, right? And it's actually going to block equal amounts of blue and red light if the planet is just a rock, right? So imagine a sort of terrestrial-like planet. It's just a rock. It blocks all wavelengths of light. It's opaque to all wavelengths of light. But of course, it's much smaller than a star. So we still get some wavelengths of light, but not quite as much, right? That's where the transit dip comes from. The planet is blocking some of the light. But if instead of that planet being just a rock that's opaque at all wavelengths, what if that planet had an atmosphere? A large sort of gaseous atmosphere. And that atmosphere was opaque at blue wavelengths, but not at red. What if the composition of that atmosphere was such that there was a strong chemical absorber that was really, really efficient at absorbing blue light, such that any blue light that would have otherwise been transmitted through the atmosphere, it gets absorbed. Whereas the red wavelength, let's say there is no chemical gas in the atmosphere that is a strong absorber of red wavelengths, so the red wavelengths do transmit through. Well, so what would happen is if you measured the transit of this planet, not all wavelengths at once, but at blue wavelengths separately from red, you would see a different transit depth, right? The transit would be deeper at blue. The planet would literally look larger at blue wavelengths. And if you imagine doing that not just at two wavelengths, but at a continuum of many wavelengths, you can start to build up what's called a transmission spectrum. So as I'm showing here, it's the planet radius. Literally, the size of the planet is changing as a function of wavelength. And all of these different features that you see are absorption by different molecules or different chemical species in the atmosphere of that planet. So this is a model. It's a model of an Earth-like spectrum around a red dwarf. And it's Earth-like because there's a very sharp O2 feature. There's these sort of broad water features. Of course, we have water in the atmosphere. There's a sort of really broad methane feature at about 2.2 microns and a little bit of CO2, sort of spit it in there somewhere, right? But these are the sorts of molecules that the Earth's atmosphere would be absorbing if you were an alien astronomer looking at the Earth's transmission spectrum. It's just a model, but this is sort of an example of a transmission spectrum. And I've just sort of highlighted the visible wavelength regime here, right? This is what our eyes are sensitive to. All of this other stuff is longer wavelength. All of this stuff is sort of infrared. Okay? They're very, very tiny variations. Right? There's some percentage variations. You don't care what the absolute transit depth is. If you want to measure the chemistry of an atmosphere, you need to measure the relative variations of these features as a function of wavelength. And on an Earth-like planet, they're very small. Okay? The reason they're very small is because our atmosphere is so damn thin. Okay? Right? This is an image from the International Space Station. So here's the Earth, right? The bulk of the Earth is the dark opaque bit. And then this very thin veneer is our atmosphere. And it's the atmosphere that's giving you that differential transit depth, right? The bulk of the planet just sort of sets the absolute transit depth, the absolute reference depth. But it's only this very thin annulus that's giving you the differential transit. And because our atmosphere is so thin, because the atmosphere of a terrestrial exoplanet is so thin, it's a very, very tiny signal that is producing the differential transit depth. Luckily, we built this thing. Does anyone know what this is? They say know your audience, but I don't want to assume anything, right? Of course, it is. It's the James Webb Space Telescope sitting in Baltimore from a number of years ago, which has since been launched, right? Launched on Christmas Day 2021, I believe. Probably the most ambitious observatory that humankind has ever built, partially with a mandate to go and do transmission spectroscopy of exoplanets, in particular terrestrial exoplanets. An instrument that's, or not an instrument, rather, a facility, an observatory that's really pushing the boundary towards finally studying the transmission spectra of terrestrial exoplanets. So this is one of the first images. I think it was released about a year ago, last July. I think the White House had a press release of the first scientific results from JWST. And this is one of the images that they showed. This is JWST, the most ambitious observatory that humankind has ever built, staring at the Hubble Ultra Deep Field, right? Looking back in time, looking back about 10 billion years at extragalactic sources. Seeing all these kind of interesting lens sources. I mean, there are a few foreground stars, but you can see these sort of like background lens galaxies. All these other distant points of light are galaxies back at the very early universe. One of the first images that JWST ever took. It was kind of breathtaking, right? There was the White House actually put on a press conference to sort of show this image, as well as a few others, to sort of demonstrate this amazing technological feat that we had just accomplished, right? With the launch and the commissioning of the James Webb Space Telescope. They also had another image. I really like this one. So this is a sort of galactic star-forming region. You can sort of see this bubble of gas, this sort of edge of this bubble of gas. It almost looks like it's boiling up. And that's because there are massive stars that are forming inside of this dust cloud that are literally pushing the gas away because they're so energetic. There's so much high energy photons that these newly formed stars are giving off that they're literally boiling the gas and the dust. And you can see these amazing intricate features with the James Webb Space Telescope. Right? This is part of that press conference. This is one of the first set of images that were being released to the public to basically advertise how powerful this observatory is. So we saw the extragalactic image. We saw the wonderful star formation image in our own galaxy. Are you ready to see the exoplanet image? Has everyone seen the exoplanet image? Yeah. So it's pretty breathtaking, isn't it? No, it's not. It's literally a damn spectrum. I thought it was pretty neat too. Absolutely. I agree with you 100%. So when this press conference was going on, I believe it was last June or last July, I was at my previous institution. I was at Harvard, and we all sort of gathered into the main lecture hall to sort of watch this press conference being streamed. And they showed the amazing extragalactic image and the star formation image. And all of my colleagues who work on extragalactic things and star formation things were, this is amazing. And then all the exoplanet astronomers were sitting here waiting for the transmission spectrum. And this showed up. And we all lost our freaking minds, right? And everyone just sort of looked at us and went, what the hell is this? This is an artistic rendition. This is not real. Well, at least the background image is not real, right? It's just a spectrum. This is all that you get. This is the sort of like pretty picture that you get from an exoplanet. Damn right it is, right? We all got really excited about this because it was demonstrating the exquisite precision with which JWST is going to be able to measure transmission spectra of exoplanets. Now, this is a giant planet. This is a gas giant planet, a sort of hot Jupiter. So not a terrestrial planet, but just looking at this, we can say this is only one transit. We can see the sort of error bars. That's what we were looking at. We were looking at the size of these error bars and saying, all right, look how precisely we're going to be able to measure transmission spectra. Such that eventually when JWST goes to monitor terrestrial planets, we might actually have a shot at getting those types of signals. Okay? So coming back to this model, yeah. Parts per million, yeah. Yeah, so is it one? It is, yeah, 200. So sort of, again, it's the differential depth that you're interested to hear, right? Yeah. 14,200, 1440, I agree. Right? But much smaller on terrestrial planets. Right? So I want to actually compare, if we come back to this model, I want to compare what was the state of the art before JWST for exoplanet transmission. It was the Hubble Space Telescope. And so this is, again, imagine a terrestrial planet around a red dwarf. If the Hubble Space Telescope were to take a single measurement of this planet's transit depth, this is sort of a depiction of the error bar on that measurement, right? It extends beyond the screen, right? It's much larger than the depth of the transmission signal itself. So HST could not do this type of science. There was no way in heck that you were going to be able to achieve the precision necessary to measure the transmission signatures of a terrestrial exoplanet, even if it was around a red dwarf. But with JWST, we get something that's much more, I don't know what the word is, but let's call it realistic, right? One where now we are starting to enter a regime where we actually have a facility that once you build up more signal, right? You can imagine doing this at many wavelengths, not just one, where we are actually in a regime now where we have the sensitivity to get at these molecular features on terrestrial exoplanets around red dwarfs. And that's what JWST is right now, is what it's pushing to do. There are a number of programs, many of which are being led by Canadians, including myself, but many in the University of Montreal, for example, that are really pushing JWST to, for the very first time, potentially detect the atmosphere of a terrestrial exoplanet around a red dwarf. Now, before I move on to the next concept, I want to just get a sense of time because I don't see a clock in this room. So, are we at 9:15? I mean, I can go for another hour, but I will not do that. So instead, what I'm going to do is I'm going to jump over quite a lot, actually. I'm going to jump over some direct imaging that we can sort of talk about here. So I'm going to go through these. I'm not going to talk about these, but I'm just going to show it to you just in case it generates any questions. So directly imaging planets is something that we can't do for terrestrial planets, but we have done it in practice. There are actually 4 directly imaged planets in this image. They're giant planets, but this is something that we want to push towards doing with really large telescopes, right? Really large telescopes on the ground that are currently being built. This is the European one, the European Extremely Large Telescope in Chile, right? It's going to push, it's big, it's going to push towards doing direct imaging of habitable zone Earth-like planets around red dwarfs, not around sun-like stars. And I'm going to skip over this figure because it's complicated and unnecessary. TESS is finding many of the closest systems that are going to be amenable to those sorts of direct imaging experiments. Right? TESS is the Transiting Exoplanet Survey Satellite. It's searching for transiting planets, ones that are going to be fantastic targets for JWST and the next generation of extremely large telescopes. I do apologize for going through this quickly. But there is one point, one really important point, I think, that I do want to spend a few minutes on. So this is a bit of a timeline for exoplanet missions. We've talked very briefly about Hubble. I think I had one slide on Hubble. There's a couple of other things that are important for exoplanets. Kepler discovered basically all of the compact systems that we know of today. And TESS is sort of continuing that legacy now. JWST is going to be great for the first time getting transmission spectroscopy of terrestrial planets around red dwarfs, not around sun-like stars, but around red dwarfs. Right? Roman is going to be launched hopefully in the next sort of 5 years or so. Going to be a wonderful demographics mission, but not really great for doing really detailed studies of individual planets. And then I've added the ELTs, even though it's not in space. I've sort of added the Extremely Large Telescope because it's going to be great for doing direct imaging, potentially of terrestrial planets, but again, around red dwarfs, around sun-like stars. So the last point I want to make is red dwarfs are great, but I heard flares. Is that the word? Yeah. I heard flares early on in the talk. Red dwarfs like to flare. High energy photons may not be great for life. I don't know about you. I don't like to spend too much time outside in the summer. just from the sort of moderate UV radiation that our sun gives off. But if the sun were flaring as often as many red dwarfs do, that's a heck of a lot of high UV radiation that my very fair, pristine skin cannot handle. Red dwarfs do it a lot. So there are a lot of very valid arguments, I would say, for why we might not expect life to be forming on terrestrial planets around red dwarfs. So what are the prospects for looking for terrestrial planets around sun-like stars? A true bona fide Earth 2.0. It's not JWST. It's not the ELTs. It might have to be a future mission, something called LUVOIR, the Large UV Optical Infrared Observatory. Something that astronomers are planning on now, hopefully to be launched in the next few decades. The community is behind this. We've recognized that this is something that we need to push for, because that second question in exoplanetary astronomy, right, that question of are we alone in the universe, really needs us to gain accessibility, observational accessibility to an Earth 2.0. And I want to argue very, very quickly for why LUVOIR is the way to do it. So it's powerful because it can obtain images sort of like this one. So this is an image taken of Jupiter with Juno. Juno was a spacecraft actually orbiting around Jupiter. So we sent it there. It took years to get there. And when it got there, it was able to take these fantastically detailed images of Jupiter with a resolution of about 30 kilometers per pixel. But we had to send the damn spacecraft there. With LUVOIR and its Earth-centric orbit, you can get a comparable amount of imaging resolution without having to send the spacecraft, right? Which means that you could easily do this. You could do imaging surveys of Jupiter. You could do imaging surveys of the other planets in the other parts of the solar system. For example, this is Pluto with the Hubble Space Telescope back in the mid-90s. With LUVOIR, you can get much higher resolution image than that. Now, maybe it's not quite as breathtaking as the image of Jupiter, but this is unprecedented. You can't get this unless you send a spacecraft. And indeed, we have done that. It was called New Horizons, which I think is where this model actually comes from. But even with LUVOIR, you can start to see these different shades. You can actually start to see hints of these different geological features on the surface of an icy dwarf planet like Pluto without having to wait decades for the damn spacecraft to get there. Which means you can also do it for the other small bodies in the solar system and start to build up those really robust statistics. But the kicker with LUVOIR is this. So this is a synthetic image of an analog to the solar system if it was located around a star 40 light years from us. And the thing is, you can actually image many of the planets in the system, right? You can see Jupiter very clearly. You can get in close to the star. So the star is behind what's called a coronagraph, which is used to sort of suppress the starlight. But you can get close enough that you can see Venus and Earth. In the next few decades, with a large 15-meter class space telescope like LUVOIR. And why that's really powerful is, well, I don't need to tell you, right? Actually being able to image, directly image an Earth-like planet allows you to start to tease out perhaps some features on its surface, right? Rotational modulation, potentially the presence of continents or oceans or atmospheric biosignatures by actually seeing light reflected by this planet. It's something that's going to require an exceptional observatory, right? Something like a LUVOIR. And even if we find it and we want to get spectra, say like this, it's going to take a lot of hours to get there. But you can imagine that if we go and we find an Earth 2.0 now with the transits or with the radial velocity method, you better damn well believe that we're going to spend as much time imaging it with LUVOIR, more time than was dedicated to the Hubble Deep Field, more time than will be dedicated to the JWST Ultra Deep Field. And that is because, coming back to this question of, are we alone in the universe? One of the most fundamental scientific questions that's been asked by humankind for millennia now. We are currently working towards building up the capabilities using something like a LUVOIR to finally get at that question. And it's not so far off. And I hope some of you are going to be along for that journey because I'm getting really excited about it. A couple of decades away is not that much longer. My knees will give out, but I'll still be here waiting with great anticipation to see those first images. And I hope you'll be along there with me, as excited as myself and my colleagues will be. So with that, I know that I've run over time. I apologize, but I'm more than happy to take questions. Thank you so much.
From here, and I'll ask you maybe to just repeat the basis of the.
Sure, absolutely.
Okay, gentlemen there.
Technology back in indirect will be more now or 20-year audit.
Yes, so the question is, what is the current state of technology as it would be applied to LUVOIR? So there are definitely prototypes for many of the types of technology that would have to be integrated into a spacecraft like LUVOIR. So for example, the coronagraph, which is the piece of hardware that you need to suppress the star's light, those exist. We've used them to directly image planets from the ground and from space already. And that is relatively new technology in and of itself, right? The ability for a coronagraph to be sensitive enough to allow for us to detect exoplanets is less than 2 decades old. I'd say maybe a decade and a half. Now, coronagraphs have been much older than that, but they've primarily been used on the sun. But the point is that in a relatively short amount of time, we've been able to push to the point where we can detect exoplanets. And so if you can extrapolate that into the future, and I think many of the sort of NASA engineers are confident that they will be able to continue on that trend, those sorts of things are definitely within reach. So maybe to convince you, or to be a little bit more convincing, there was a document, every 10 years, there's a document that comes up from the American astronomical community called the, in Canada, it's called the Long Range Plan. In the US, it's called the decadal. Thank you. Yeah. And so the decadal makes recommendations for what the United States astronomical community, the largest astronomical community in the world, should be funding and what big questions it should be pursuing. And the biggest recommendation was not necessarily LUVOIR explicitly, not that it has to be exactly this thing, but it has to be some concept loosely based on LUVOIR, specifically to get at the ability to image an Earth 2.0. And that decision is not made lightly. That decision comes from years of consultations with engineers and scientists. And after all of that consultation, which is way up here above my pay grade, the consensus was that this is what we have to do. And for that reason, I do believe that the funding is going to be available to fund the sort of technology and development to ultimately do that thing. There are many other things that we would like to do, some of which are either lower priority or a little bit too ambitious at this point in time. In the decadal 2020, LUVOIR was decided, it's the thing. The time is now. We're going to get there in the next few decades. Yes. Yes, so, but specifically in the radial velocity context. Yes, so one planet will sort of make a nice sort of sinusoidal modulation, all right? If you were to add a second planet into that system, it would have a different time scale, right? Because you can't, I mean, if you ask the dynamicist, maybe you can have 2 planets in the same orbital period, but it's not really a stable configuration. So in general, you would expect to have multiple planets with different periods. So they would create, maybe this is one sinusoid, and then on top of that, you would have a longer period sinusoid, or maybe a really high frequency one. And you basically are looking at the superposition of those signals. And so if you build up enough data, you can actually start to distinguish between those different frequencies. But it does make the problem more complex, I agree.
Done a velocity method, what solar system would look like before we were 20 years away?
Indeed.
I sure with our selection plan, different masses. Pretty messy curve.
Yeah, it would be an exceptionally messy curve. There's one signal that would dominate it by far. Jupiter. Yeah. So Jupiter on the sun induces something like a 12 meter per second signal. As you go out further beyond Jupiter, of course, the planets become less massive. First by like a factor of 3, I think, to Saturn, and then by more than an order of magnitude when you get out to Uranus and Neptune. They're also further away, so that also makes the amplitude smaller. So they're lower mass and they're further away. They're significantly smaller signals. The terrestrial planets, although they're closer, are hundreds of times less massive, and they create really tiny signals as well. The Earth, for example, well, we said we said Jupiter is 12 meters per second. The Earth is 9 centimeters per second. Yeah. So if you have our current technology, which is sort of good to the level of 1 meter per second, you can really only detect Jupiter and Saturn, and the rest would all be buried in the noise. Now, in reality, of course, those planets are invoking some gravitational tug on the sun. So in reality, that signal is there. But would we, as an alien civilization 40 light years away with our current technology, be able to detect it? The answer is no. We would only see Jupiter and Saturn. And so that's not a terribly hard problem. We have lots of examples of multi-giant planet systems where we can detect signals at the level of 12-ish meters per second. 20 and more, yeah. I ran out of ideas.
If you run through the mass experiment paradox, using that and more, and you're getting close to 10 to 20 seconds.
So I would argue that if you fold in all the factors that go into this, so the question is with regards to the Fermi paradox and trying to estimate how many inhabited planets there are throughout the galaxy, or I guess throughout the observable universe, if the question is 10 to the 22, there are a number of different terms that go into that expression, right? Things like how quickly do stars form within the galaxy? How many of those stars are actually forming planets? How many of those planets are, Earth size and Earth's temperature? Those sorts of questions are observationally accessible, but then you have to keep going, right? You have to say, even given that number of Earth-like planets, how many of them are forming life? We only have one example of life formed in the entire universe at present, right? And then beyond that, even if the life forms, does it form complex multicellular life? Beyond that, does it form intelligent life? Beyond that, does it form life capable of communication such that we might actually be able to talk to each other and know that each other are there, right? Those sort of additional factors, we have zero constraints on as far as I'm concerned, right? And if even one of those factors is unconstrained, then you cannot confidently calculate the number of inhabited planets throughout the galaxy or throughout the universe. Okay? So I say we can play that game, right? We can have that conversation and make guesses, but you might say, you might say that the probability of a genesis on another Earth-like planet is 100%, and somebody else might say it's not 100%, it's 10 to the minus 10%. And neither of you would be right and neither of you would be wrong because it's just speculation at this point, right? So I hesitate to answer the question because the point is that no one in this room, no one anywhere can confidently answer the question, right? But we can definitely have the conversation. So there's a lot of work in the astrobiology field about, yes, even if we had Earth-like life, right? Even if the biosignature that you're after is, say, O2. Right? Imagine it is life like our own, and it's photosynthesis that is producing that biosignature. Even if we were able to go and detect molecular oxygen, which we might be, not with JWST, but we might be able to do it with the ELTs on the ground. The question is, how can you distinguish that molecular oxygen as being a byproduct of biology versus some abiotic process. So the astrobiologists are thinking a lot about, say, geological processes or astrophysical processes that could create molecular oxygen that, if we were to go out and detect molecular oxygen, would we be positioned well enough that we could distinguish between an abiotic production versus a biotic production? And so that's a lot, that again, that's a field of active research. And the answer to that is probably, we don't need just one biosignature, we probably need multiple biosignatures that in tandem, you can imagine as you add more and more biosignatures, it becomes harder to create that chemical configuration without something as disruptive as life. Life is a very disequilibrium process. And so these are the types of goals we're sort of going after with the search for atmospheric biosignatures. Indeed. So there's a lot of work. Actually, there was a lot of work at McMaster before I arrived there that was tackling exactly this question from a theoretical perspective. So from an observational perspective, we have, for many years, there have been a number of campaigns that have been searching for what we call exomoons. And I would say that there's been no definitive discovery of an exomoon yet, although there are a few candidates. And there's one major candidate in particular, and it's very different from say the Galilean moons around Jupiter and our own solar system. So this very prominent exomoon candidate, right? So not confirmed, but a candidate is a Neptune-sized moon around a Jupiter-sized object on a Jupiter-like orbit. So a long period orbit that you see the planet transit. We've seen a few transits, because again, the period is really long, so we don't have that many. But when you see the planet transit, there seems to be this sort of anomalous transit that goes along with it, although sometimes it's out of phase, depending on which transit that you're looking at. And the depth of that feature corresponds to a Neptune-like sized body. And it seems to be co-orbiting with this Jupiter-sized planet. Okay? So if that is true, if that truly is an exomoon, it's a moon that is vastly different from the types of moons that we have in our solar system. Right? If you ask the theorist, if you think from a planet formation perspective, do you expect to form Neptune-sized moons? Right? Neptune is 4 times bigger than the Earth, and the Earth is bigger than any moon that already exists in the solar system. So do we even expect those objects to exist? And the answer is kind of maybe, right? But this is a sort of limitation in terms of accessibility. The only candidates we have are very large objects, much larger than the sort of moons that we have in our solar system. So if there are analogs to, say, the Galilean moons out there, they're sort of beyond the sensitivity limit of what we've been able to do so far, unfortunately.
Great. Well, thank you very much, Dr. Cloutier, for
Thank you. Thank you.
I don't know if you come down and make your announcement. What we're going to do is we're going to make a few announcements, and we're going to shut down the Zoom thing because I'm afraid this laptop is about to start to ignite on fire. So just we have Riverwood Tuesday night at 9 p.m. So please let us know. And our next meeting is June 9th, our focus meeting.
Hi, everybody. For the membership who's attending today, we sent out a notice for our picnic, which is supposed to happen on 10th of June. We're introducing the Astro Exchange, where you have the opportunity to bring in perhaps some eyepieces, perhaps an old telescope that you haven't used in a while, a pair of binoculars, some books. Bring them out, perhaps make a little bit of cash to take home with you. The benefit is really you do a little bit of spring cleaning. And for the new members, perhaps they might pick up something at a much cheaper cost than, they would have to spend in the store. So really encouraging, if anybody has something to clear out, to submit their names. The only reason we're asking to submit the names is because we have limited table space. If you're bringing out a table, that's even better. I have left a little piece of paper here for those in attendance. If you want to quickly sign up, again, it's free of cost. You take the cash home. Also, if you're bringing stuff that cannot be given to somebody, please take it home with you. That's important because we have no way of, giving that away to somebody else. If for those who are on Zoom, feel free to send me an email. I've sent out a couple of emails, just respond. And, we would love to have you. So we are extending the sign up till 9th of June versus the 2nd, just to give people more time to perhaps go look at their basements or what have you. Thank you very much and look forward to seeing you at the picnic.
Thanks, Swapna. Yeah, just to remind everyone, the picnic, there will be an announcement probably in the next couple of days. Val and Alan Connery are just a few hours away from coming back from their holidays. So they'll be sending that out to everyone very soon. So again, thanks very much. And I think our speaker will be here for a few minutes if anyone here wants to ask any more questions, but I'm going to close the meeting down now before things get exciting. So thanks very much.